Good morning, everyone. Welcome to the EasyPower Tuesday Refresher Series. My name is Jim Chastain. I'm Applications Engineer here at EasyPower. And this seems to be a popular topic, understanding harmonic and PowerFlow and EasyPower. And as far as a disclaimer, though, in the time allotted, this is tough to do extensive analysis or even a demonstration of these tools. But hopefully what I'm able to show here is both entertaining and enlightening. So welcome everyone, and as we like to start our sessions each week or each webinar, I would invite you to participate in a poll question. And obviously there's no obligation, but we do like to kind of get a sense of where people are coming from as we get into this topic. So if you would please participate responding, and certainly do appreciate everyone joining us. I realize this time of year is a little bit busy, and sometimes it's difficult to make time for doing research or expanding horizons such as this. So it looks like we got close to a quorum. We'll leave this open for another 5 seconds. And here's how people have weighed in on this. So it looks like primarily we're coming out of this as a possible potential for expanding our capabilities. So that much I appreciate. And same question basically applies to harmonics question. And this is something that's coming up more and more frequently. Invariably, a concern about harmonics is the last thing that floats to the top when we're trying to troubleshoot a problem with the factory. And it's nice to have at least an understanding of what the tools can help with. But as in most cases in life, they really don't have a panacea. It's really, frankly, just that, a tool. And the hard work has to be done by the person using the tool. All right, let's share this. And it looks like it's pretty much what I expected. So again, thank you all for participating. And let's jump into the material at hand. As I mentioned, it's difficult to be comprehensive about either of these two topics. The EasyPower offering falls into two basic spheres. Worst case survival, which applies to the short circuit, coordination, and arc flash modules. And in some ways, there's less of a need for accuracy because we're talking orders of magnitude larger numbers in terms of the fault current that we deal with. In normal systems operations, where we'd see the use for power flow or load flow analysis, being more precise is an attribute or a benefit, and there's some work involved in getting that done because it's not something the tool can do on its own. It really based upon how much data we have to work with. So when we talk about power flow specifically, what we've generated with a short circuit model is best called an ideal model because what we've used is nameplate data. And as far as the loading, the default setting in EasyPower when you put a load on the one-line diagram is 100%. And now that can vary from time to time, and it makes it difficult to sit there, especially when you're designing a system and knowing what the load settings will be in real time. So there's a need to have data alignment, and primarily this can be done in EasyPower one of three ways. You can manually scale groups of loads or individual loads in the PowerFlow tool itself, or you can enter the data that you've collected with the data logging equipment, which often it can be portable, or in some cases you can import SCADA data if that's something that you have access to. And frankly, it takes a little bit of effort. It's not just a one size fits all, but it's a way to save time as far as this scaling process. Then there's also the need, and what I'm going to show here is an example of what I call adding virtual loads, because frequently when we're doing the short circuit one-line diagram, we do make assumptions and take some shortcuts as far as the details on the loads, and that's an area that can be troublesome if we're trying to look at load flow and the more, if you will, the better accuracy of the results. So I'm going to jump into EasyPower here and look at a system that we've had the ability to take some measurements. And initially when we set this up, we were at 100% load on the motors. And as we go into PowerFlow and then solve for the results, frequently in PowerFlow, we might want to just look at the branch flows in amps to see how accurate or rough order magnitude where things are. The problem is we can see large results. For instance, we measured 550 amps on this main and 300 some odd on the feeder, and it didn't really match up, or doesn't really match up with the prediction from PowerFlow first pass. So more accurately and more beneficial is the ability to look at the real and imaginary current, or the kilowatts and the kilovars, as it flows through our system, because that's what's really driving the PowerFlow equations. So what we see here is we measured 359 real kilowatts of real power and 281 kilovar. We had pretty accurate readings on this feeder for this large motor, but we see a large variation here where we're reading something over 100 kilowatts, but our model is only showing 8. And so and it kind of looks like this if you get back to PowerFlow. And so what we're looking at is a need to align what we're modeling versus what we're reading. So we measured actually in real power 359 kilowatts and imaginary power 280 some odd. On the left side, we had good alignment with what our model is showing. On the right side, as I mentioned, we're kind of off by a factor of 100. So what I'm going to do is add a virtual load to make up for that, because the real system isn't that accurate versus our model. And the way that looks in EasyPower, as we kind of go back to the model, is I've set up a virtual load here, and I'm going to do it in the database edit. And just because I know what the missing data is roughly 100 kilowatts and 100 kilovars, I set those up as constant loads. And now when we go into PowerFlow and turn on that load, we get relatively good alignment in our readings. So now, and again, the result is, first of all, we want to know why this much difference exists. If we're aware that there's some loads that we didn't factor into the short circuit study, that's one solution. But as far as the benefit of PowerFlow results over time, the more accurate these are, the better off we can be. Now, if you kind of jump back into EasyPower, back into my slideshow. So that's a technique of balancing the loads. Now, what is happening in PowerFlow is actually we're looking at a balanced situation where the power drawn by the load varies with the voltage, and then the current that's consumed by the load will also vary with voltage. And so there's an interaction between the current drawn, and the power produced. And in a computer, this is basically comparing two sets of equations against each other. And because these are vector sums, you basically assign some value to start with and then converge on a solution that you can control in EasyPower. So the whole purpose then is to have a result that approaches a conversion point that's similar to what our real system looks like. In applying that to a larger system, we may have some problems with the convergence. And so the technique is to isolate, just as I did on that virtual part, isolate certain parts of the system, determine what's causing the issue, and then drill down into the mistake that's been made. And part of this is essentially tuning the database, but it gives us a better result. So what we're looking for as outputs then from our PowerFlow analysis is the voltages that should be read at each of the buses, the generator data in terms of supplied power versus voltage drops, the load data, the branch flows. A nice output is power factor to keep us in good graces with the utility company. And then the ability to trend and compare the losses, either in the current flows through the branches or the voltage drops at any particular bus. If you track those and the delta between the model and the real system, that could give us an indication where we have a trending issue that merits preventive maintenance, or at least locating the source of the difference over time. One other factor that's particularly useful comes up almost without emphasizing it, and that's the ability when we're doing a new design or an extension to a plant, the effect and the need to have transformer taps to minimize the power drop or the voltage drop coming into the system. So a good example of that, and this just came up here a week or so ago, when I'm working on a new design, how can I anticipate what that drop is going to be across the initial transformer or any given transformer? So if we go back to EasyPower, and I'm going to open up let's close this one out and open up. So let's say we've completed our design and we want to see what's going on as far as the voltage around the system. When we go into PowerFlow and solve, we see that we have almost a 3% drop in voltage before we even get to any of our loads right off the transformer. And then in addition to that, if we have any remote loads, we're having more voltage drops through those, or losses through those cables. So the question is, how can we deal with that? Well, putting in more cables to reduce the resistance here isn't necessarily the thing to do. The tool itself will show us the voltage drops at each bus. I'm up here on the top row. The generator data and load data, both in real power and imaginary power, and then the branch flows. The part I want to look at is, in voltage violations. And so if we have something that's dropping beyond a certain threshold, the tool can flag us on that. What I want to deal with is this initial drop, albeit not that great, but because it's something that's affected by the tap settings on the transformer, what is the correct way to deal with this? Well, the technique that's very productive and easy to explain, if I go back to my database edit, as I'm setting up this transformer, again, the default setting is to just have a 1-to-1 tap ratio when we set up the transformer. However, if we set the transformer up and indicate that has a load tap changer involved, and we want to adjust the from side and we want to control the voltage at the to side, right? We want to see what the results of that load tap changer would be, finding the quiescent point for the system. So when I go back to PowerFlow and solve the equations, now we see that the tool has automatically changed the tap settings. Now if I start out with a 13.469 tap on my input and 0.48 on the output of the transformer secondary, then I can maintain a better voltage at least at my first loads. and it'll matriculate down the rest of the system. So once I've got that determined, now 13.469 is the tap that I want to use. I can go back to my database edit and change the tap then here to 13.469. And with some, now the same thing is true if I have a spread from a utility company where it may be seasonally adjusted, and if I don't want to put in a load tap changer, automatic one, I want to just find a common setting for taps that will survive or keep the plant in the best case condition optimally over the seasons, then I would run different scenarios with this same technique and probably find a happy medium as far as my tap settings. But now when I go back to tap settings, I'll have my 13.469 and resulting in my better voltage on the secondary of the transformer. Okay, so again, what we're looking at as far as the outputs in EasyPower PowerFlow are basically, jump back, elements that are useful or more useful in the real world and day to day. And there was a time back 15, 20 years ago when this would be a weekly analysis indicating a trend in any of these sections, and facilities engineering would basically live and breathe understanding what the power flow results are in their plant, if not on a daily basis, certainly on a weekly basis. And with the rise of short circuit analysis and arc flash, there's been somewhat of a lack of focus on this element, but it's extremely valuable in optimizing my system. Okay, jumping into harmonics, the same discussion applies, whereas the short circuit model that we created is not that helpful because we did start off with 100% load, and usually we don't have harmonic data as part of the database. So if we do take pains to input that data, it does have the ability to show us potential sensitivity to harmonic interference, and especially when we're considering making changes in the system that involve nonlinear loads or nonlinear control systems, it can identify areas that may be sensitive to those problems. And so what I'm going to run through here is the issues involved when I have to deal with power factor correction, VFD conversion, and we're going to look at the summary results, the frequency scan capability, what happens if I inject a certain frequency harmonic, and how it affects the rest of my system, and then some techniques in VFD filtering that involve phase shift cancellation rather than just building more of a filter. So if I jump back into my, and again, this example is one that's in your installation if you have the tools. What we're looking at is a relatively large system, and what I like to start with is just looking at any place that there's caps, especially in an older facility, because in 15, 25 years ago, when we designed a system, there was really no, I want to go up and find a filter cap. So let's find cap 3. When this system was built, this capacitor bank was put in there for one of two reasons or both, and that is to raise the voltage level so that we had better efficiency on this motor, and or to contain or restrict the losses that would be in the system if we had to deal with reactive current flowing all the way back to the utility. And so the purpose would be power factor correction. So if we go into PowerFlow, and we want to go into harmonics, and we look at a summation, what we see in this case, I've got my D rating set up, what we see is total harmonic voltage distortion, which is on the oblique, and my total current distortion, which is in line. So let's take this off. I want to go back a half a step before I look at the VFDs. So normally, or originally, I had this set up with just an induction load. And when we go into harmonics and we look at our summation, we can see that we have relatively benign voltage distortion and virtually no harmonic distortion. We do have a lot of reactive current. And as we look at the current flow, we can tell that this harmonic creates some sort of resonance. So to look at the resonance that's going to be on this particular bus, just by the fact that we added that capacitor, we can see that it exists now here right at, looks like the sixth harmonic. So back in the day when this facility was built, there was no intention of having anything outside of 60 hertz circulating around our plant. And so this type of resonance really wasn't causing a problem. Well, when we come back to today, where there's a reason to push towards VFDs, if we want to simulate what that impact would be, we come to our motor controller, we make it a VFD controller, and now we input from the equipment library a typical harmonic distribution or pattern spectrum. And so we're going to say this is a typical industrial application of a pulse width modulated system at 65% load. And so just looking at these numbers, we can tell we're going to have potentially an issue at that fifth harmonic because the current contribution, harmonic contribution, is so high coming from this type of a controller. So as we go back into spectrum, and we can look at that same frequency distribution, which I did initially, you can see we have a large harmonic distortion in the voltage values and a large harmonic distortion in the current. If we come up and look at, if we don't select a single bus, but we look at everything, we can see that there's a fair amount of distortion that's being carried through the system. Normally, a transformer operates as somewhat of a filter, and in this case, because these are such large values, it doesn't filter enough. So the question becomes, okay, well, what is the filter content or frequency content, harmonic content, let's say on this bus? So I'm going to create a bar chart, and we're scanning here from the second harmonic up through the 20th harmonic. And even on this second bus, I can see a fairly healthy fifth harmonic content because of that VFD. So that may be something we want to take into account before we even make the conversion. Likewise, there's the potential for that extra harmonic content to give us a problem in transformers if they haven't been properly sized or derated. And so the tool shows us, I'm on the top row up here, the K factor that's required or is suggested for my transformers in this particular system. And I can see the K factor here is 68.3, which is huge compared to what it was before we had this motor in there. If I come back and look at before we went to the VFD, and we'll see that effect here in other places. So anyway, so this is something we may want to take into account, especially as we're looking at doing a conversion. And part of that problem, frankly, is that we have the capacitor in the loop when we have a resonant at that point. So if we take the capacitor out, it moves the resonance point, but now we have the frequency content that's been reduced in our transformer, but we still need to be considering derating. And if we come back to the bus up here and scan it, we can see we still have a fairly significant contribution, although it's an order of magnitude less than it was, and it's slightly shifted in different frequency. So again, this is not absolute because I don't have all these other values necessarily put in there. The tool will give me my So here's a couple other ways to approach it. What is the effect of having this much contribution, frequency contribution on this particular bus? Let's try it again. So the question is, I have a large contribution here at right at the 7th harmonic. So what part of my system does that also affect? To deal with that, I want to do a single point injection. So I'm going to pick out a certain bus, and in my harmonic options, I can control the frequency that I'm injecting that current. So if I'm looking at what the impact is of a 7th harmonic injection at that bus, I can select the bus, do a single point injection, and now I can see the effect if I have that frequency on the bus and the need to filter it in the rest of my system. All right, so I'm up here on the top row. We could look at a summation for the whole system. We look at a bar chart for a single bus or the content for a single serial conductor. And we can also look at an all source. If we do have the harmonic content for each of our loads, we can look at an all source result, and this will show us the total harmonic distortion for the voltage, which is relatively low in this case, and the current distortion on each of the branches. Now, I know I'm kind of skimming through this, but the idea is that there's a lot of capability here that applies to more than just one part of the system. And a case in point would be a VFD bank. Let's see if I want to find a transformer. I think it's 12. So here we have a VFD bank, and these are actually all control drivers, rectifier control drivers, for 3 different parts of the same motor. And what they're set up for, if I go back to my database edit, I can see that they're set up for a 6-pulse driver rectifier that's shifted by 10 degrees from each other. So here's a 6-pulse controller at 0 degrees on a delta-delta setup. Here's a 6-pulse weighted delta with a 10-degree positive, and then a 6-pulse delta Y, which would produce a negative 10-degree comparison. The idea being now, if we come back to my harmonic simulation and we look at the summation of everything, we're seeing 135 amps of harmonic current in each of these legs, but when they total out, there's less than 75 amps total. So we're actually canceling the different phases, and part of the solution requires a K rating that accommodates these harmonics for our drivers, and you can see the difference it makes when I take out one of these legs. So if I reduce that leg that was at 0 phase, you can see it actually doubles my harmonic content as a result. So this is a method of phase shifting the pulses and canceling the harmonics that are a result of it. And so that's one mitigation technique that we can simulate, and that saves us because it can be done as part of the drive system in the VFDs. Another option would be to filter the frequencies if we don't have that large of a load or that concentrated of a load. We might apply frequency filtering on certain buses. The tool allows us to put that in and simulate different values of the filter. If we go back to our database edit, we have the ability to design a filter with some fairly significant capabilities, and this can include a sophisticated combination of resistance, impedance, inductance, and capacitance. And again, before I go out and spend the money to build it, I'd want to simulate it and see if there's any side effects that maybe I haven't taken into account. So a lot of capability in the Spectrum module. It it's difficult to say what is useful to any particular problem, because harmonics are literally the last things you give any thought to as far as causing a problem. But things like overheating transformers, a high current in a single leg that's not necessarily a ground fault, and especially if you have a high concentration of non-linear loads or drivers that have been introduced new to the system, are reasons to be considering harmonics as a possible solution to the problem. So what we've shown is basically the ability to use PowerFlow to optimize our capacity of our system, identify potential hotspots, deal with power factor issues if we have large inductive loads, also assist in design for component sizing and tap adjustment, and then more based upon whether we're in the new design phase or doing addition to the existing system. Likewise, in harmonics, we can use it to identify sensitivity in our system to certain frequencies, and we can verify if it's a distortion that would be of concern even out to the grid restrictions. It gives us the ability to understand impact when using nonlinear loads, especially in a new design or an older system. We can see, verify the need for transformer derating, the costs there involved. It's better to deal with it on the front end of specifying a transformer rather than afterwards when you have heating caused by the excessive harmonic content. And then we consider the mitigation options of either filtering or phase cancellations based upon what type of drivers we're using. So that's basically an overview of what these two modules allow us to anticipate and take better advantage of the one-line diagram that we've drawn. And the more we can align it with our physical system, the more we can recover as far as investment in that effort. So appreciate everyone joining us today. I would encourage you to look into the newsletter or on the EasyPower website. We have the early regional training location set for next year. And if you haven't already, check out the online training capabilities or offerings, which can be very effective and offer a significant amount of cost savings. Thank you for joining today. Sorry we didn't have time for questions. Any questions that came in, be more than happy to answer via email afterwards. Have a good day.